Okay, so if I take a sample and I throw it in a mass spectrometer, typically what they do is you can hit it with a laser and it atomizes it, throws it into the gas phase, and it flies through the machine and it hits a detector, okay? And it says the last spectral line represents the intact molecule. What is its molecular mass? Okay, so what would you say approximately is its molecular mass?
72.
72. Okay, and then the unit they gave us here on the x-axis would be what you would put after it, okay, which is atomic mass unit. Draw an arrow to point to the spectral line that represents the mass of the outlined fragment. Okay, so you've got 2 carbons and 5 hydrogens, so you've got about 24 plus 25, so like 28-ish. Okay, so where would you draw your line?
To that group, like to the left of 30.
The left of 30 somewhere, so like somewhere around here. Okay, and why do you think there are more of some fragments than others? So if I hit something with a laser, it's probably going to break where the weakest bond is. Does that make sense? So that would explain why there are more fragments than others, because there are weaker bonds that break. Okay. Okay, so why do we care about a mass spec? Well, we can get the percent of each element in a substance with mass spec data, and then we can use that to calculate something called an empirical and a molecular formula of a substance. That's what we're going to be doing today. So let's take a look at percent composition first. This is really easy. Percent composition is where you calculate the percent of each element in a compound, and we use the molar masses in order to do that. So basically, this is going to be part over whole times 100. So if I give you something like calcium sulfate, and I said, okay, I want you to calculate the percent of oxygen in calcium sulfate. There's 4 oxygens, so the mass of 4 oxygens would be my part. The whole would be the mass of the entire compound, calcium sulfate, and then we multiply by 100, and you're done. Okay, so let's take a look at the next page. Your book tends to kind of give a little more information than they need to when calculating percent composition. So I'm going to skip the sample problem and I'm going to jump straight to the practice problems. Okay, so let's take a look at number 2, and then we will do number 3 as well. Number 2 says you've got ammonium sulfate, a common fertilizer used to lower the pH of soil. And then they want you to calculate the percent composition. So anytime they're asking you to calculate the percent composition, you will calculate the percent of each element in the compound. Bless you. And sometimes they may ask you to calculate the percent of a particular element, and that's fine. You just have to do that. So here we're taking a look at nitrogen. I've got 2 nitrogens. So it's going to be 2 times 14.01 for nitrogen. Divide that by the molar mass of the entire compound. So I already calculated this for you. It's 132.17. And then we're going to multiply by 100. Okay. I'm going to round these to the nearest whole number. Okay. So this is going to end up being 21%. Why don't you calculate the percent hydrogen? And we'll see what you come up with. Okay?
Yeah.
Oh, yes. Perfect. Thank you so much.
Yeah. Yeah.
My guys from Brophy, are you driving here?
Yeah.
Okay, you're allowed to park in our parking lot.
Oh, okay.
Because all the football players are going to the.
Yeah, I heard there is one because the pop was full.
Okay, yeah, you're allowed to park in our parking lot.
Okay, good, thanks. Okay, I got 6% oxygen. Did you guys get that? Yeah? Okay, now, if we're gonna calculate the percent sulfur, I've only got one sulfur, so 32.07 divided by 132.17. And this should end up being 24% sulfur. Okay, now, ideally, your percentages should add up to 100. Sometimes, depending upon rounding, they may add up to 99 or 101. Okay, and that happens all the time. So here what you could do is you could either do it the long way and calculate the percent of, this is hydrogen, isn't it? You could take all of these percentages, subtract them from 100 and get the percent oxygen, or you could do it the way that I just showed you. Okay, so for instance, if I want the percent of oxygen, since I've got 100 is what they all add up to. So minus 21, minus 6, minus 24. And then that's going to end up giving you 49% oxygen. Does that make sense? When I calculated it the long way, I got I think you get the same thing. So 4 times 16 divided by 132.17 times 100. I got 48. Okay?
Is one of those right? And wouldn't that be about right?
I mean, if you subtracted them all from 100, since we rounded to the nearest whole number, I would expect that to be a little bit off. So I wouldn't sweat it. Okay? Especially if you're doing the work on paper. Okay? Question?
Would we still round it to sig figs for this one?
I think I usually ask you to either round to the nearest whole number or I tell you where I want you to round. Okay, round to the hundredths place, round to the tens place, whatever. Okay? Okay, I want to do one more because this one's a little bit different. It's number 3. It's a hydrate. Okay? So anytime you've got water attached to something and they ask you to calculate the percent, make sure that when you calculate the molar mass, you are actually adding the molar mass of those waters. You don't multiply the molar mass. Okay? So we want to calculate the percent of water that's in magnesium sulfate heptahydrate. Okay, so since I have 7 waters, it's going to be 7 times the molar mass of water, which I happen to know off the top of my head is 18.02 because it's 2 hydrogens and 1 oxygen. Okay, and then you divide this by the molar mass of the entire thing. So magnesium sulfate is, let's see, 24.31 plus 32. So this is 120.38 for the magnesium sulfate. And then we're going to add that to 7 waters. So 7 times 18.02. So it looks something like this. And then you multiply by 100. You're going to end up getting 51.1, so 51% water. Okay? Does this make sense? Yes? Let's turn the page. Okay, that's pretty much half of this section. And the rest of this is empirical and molecular formulas. Okay, so now what we can do is, let's take a look at a couple of terms. The simplest ratio of each element or different type of atom in a chemical formula is called the empirical formula. Okay, so they usually call this the simplest ratio. If I multiply that simplest ratio by a whole number, I get the molecular formula. Okay, now sometimes the molecular formula is the same as the empirical formula. The molecular formula is the actual number of each type of atom that's in that molecule. So let me give you an example. An example of an empirical formula would be something like CH. Okay? If I take CH and I multiply it by 4, I'll get C4H4. That would be an example of a molecular formula because it's a multiple of the empirical, okay? Now, the structural formula simply shows you how all the atoms in the molecule are bonded to each other. That's it, okay? Reading them and deducing what you have from them is a really useful thing to be able to do, okay? So let's take a look down at the quick check. Let's come down here. And you'll see that they gave you, sorry, it's moving so fast. They gave you the 2 examples of structural formulas, okay? So in order to get the molecular formula from here, we would count how many of each atom there are. So we start with carbon first, then do hydrogen, then oxygen. Technically, there is a proper way to arrange them. We're not going to really go over that because ours aren't going to get any more complicated than this. But you'll notice that I have 1, 2 carbons here. So for my molecular formula, I would simply write C2. How many hydrogens do I have?
4.
Yeah, 1, 2, 3, 4. So you're going to write H4. How many oxygens?
2.
2. So this would be O2. Okay. If I want to get the empirical formula from here, I need to simplify all of these subscripts. So I need to have them divisible by the same number. Doesn't 2 go into all of them? So therefore, this would simplify to CH2O. Done. Okay. Why don't you do the next one? Let's see what you come up with. Okay. Did you get that? Yeah? Cool.
In the structural formula, what's the significance of 1 line versus 2 lines connecting?
Single bonds and double bonds, which we'll learn about later. Yeah.
Does it matter what order you put elements in, like carbon, hydrogen, oxygen, or could you do it like in a different?
For you guys, generally speaking, you're going to see it in the order of CHO. Depending upon the type of substance that it is, you may see the H and the O transposed. I'll go over that when we start looking at structures. Okay? Okay. So now what I want to do is I'm going to teach you how to use the percent composition to calculate empirical formulas. So we're going to jump straight over here. And then do you guys have your review packet for this chapter handy? Because I believe I typed up the steps for doing this in your review packet, and there's no sense in you writing it all over again if you've already got it.